So as I mentioned, this is part 3 on the introduction to systems engineering. So that's what we're going to be looking at today, as we've been doing for the past sessions. And the topics that we are going to cover this morning are coming from these two references on red in the slide. So the engineering design of systems and also your textbook for the class, which is Systems Engineering Principles and Practice. And here's the list for the agenda for this morning. We're going to talk about the perspectives of systems engineering, then what are the domains, basically what are the areas that are part of this profession. Then we're going to talk about systems engineering fields, systems engineering approaches, and finally systems engineering activities and products. So what are the things that we basically produce after we implement these concepts? So let's start with the first one, perspectives of systems engineering. And some of the things that I'm going to discuss this morning I have mentioned now and then in the first few lectures. So a spectrum of view exists in understanding systems engineering, from a general system thinking approach to problems to the developmental process approach for the actual discipline, which is systems engineering, to the broad perspective of engineering systems. So three areas, combination of this concept of system thinking, basically that we are considering not only the individual components, but also the actual system as a whole, how everything connects, how everything affects the actual product. The engineering component, which basically we're solving a problem using a new approach, to the actual profession of systems engineering. So let's talk about each one individually. So when I mention systems thinking, this is an approach to a problem that examines the domain and the scope of the problem and defines it in quantitative terms. So system thinking looks at the parameters that help define a problem through research, surveys, and also develops observations about the environment where the problem exists. So remember that we are going to be dealing with the interfaces for our system, and we have to take into consideration the environment in which the system is going to behave. As we did in the case study, you notice that there were some things that were not considered. When you put the system together and you put it in a certain environment, we expect the system to perform as we have designed it to, but that's not the case every time. So we need to make sure that we consider all the possible variables that can affect the performance. And we're going to generate options that can address the problem. So when you're designing a new system or for a new problem, you're trying to come up with a new solution, there's not going to be a single design. You're going to be looking at multiple designs, and then you're going to make a trade-off analysis and make sure that you design, but you select the best option among them. So in terms of systems engineering, the actual discipline focuses on the products and solutions of a problem. And that's one of the first things that we discuss at the beginning of the semester. That's what we do as engineers. We solve problems. So we are focusing on the products. What are the things what are the systems that we can design that can help solve this problem? With the intent to develop or build a system to address the problem. The approach tends to be more technical. So we are going to be using different tools, seeking from potential future users and developers of the solution system. So what are the top levels, needs, requirements, and concepts of operations? We have to take into account, again, the customers, what are their needs, what are their requirements, and what is the environment. Attention is given to the subsystem interfaces and the need of viable and tangible results. So one more time, the interfaces are coming into our discussion. It's very important for the type of system that we are going to be targeting. They are complex. There's no way that you can come up with a system that is going to be based only in one single product. So most likely you're going to be dealing with different parts, different subsystems. So how do you integrate all of them? Make sure that you have the right interfaces to connect them. And then we get into the engineering system. This is a broader and robust perspective to systems approaches to solve very extensive, complex engineering problems, integrating not only engineering management, but also social approaches, social science methodologies. So now we are involving the population. So it's not just I'm going to engineer like a cell phone, or I'm going to come up with a new CPU system. Now we are looking at problems in this field, engineering systems that are connected to the actual population. So for instance, I'm going to be presenting some examples in a second. So the intent is to tackle some society's grandest challenge with significant global impact by investigating ways in which engineering systems behave and interact with one another, including social, economic, and environmental factors. These approaches encompass engineering, again, social science, and management processes without the implied rigidity of systems engineering. Excuse me. So here's an example. This is coming from a couple of years ago, the Ebola outbreak. So this is a very complex situation that we faced a couple of years ago. So we're seeing these cases of the Ebola in some patients, and we were trying to somehow limit the expansion of this outbreak. So if you remember this was a very difficult situation. Most of this news are from 2017, I'm sorry. So at the beginning of 2017, so this is a type of problem in which you don't only need to consider the social aspect of the behavior of the population, but also there's some engineering aspect in terms of how are you going to be treating these patients, how are you going to be locating these people so they don't, you limit their contact with other people. Also, how are you going to devise some medicines that they can help the patient to get better so they don't die. So there's a lot of components, the social, the engineering part, and so on. So here's Ebola map as Thursday, January 2017. I don't think you can see that, but so a year and a half ago, we were having in red, there were confirmed Ebola patients. So if you can see in this part of the map, and this is kept online, it's live statistics, but this was for a year and a half ago. There were a couple there were actually 3 patients of Ebola close to us. And this keeps track of how many people have died, how many people are suspected to have the disease, and so on. So as a year and a half ago, the mortality rate for this disease was 70%. So if you had this, you were very, only 25, about 29% chances of actually make it. So this is a very, very complex problem. And a lot of things went into this. The CDC got involved. There were people from, I met a couple of professors that were involved in this, working with the CDC, industrial engineer professors that were targeting and trying to control the spread of this disease a year ago. And so it's a combined effort, and this is the type of problem that we're referring to when we're dealing with engineering systems. It's not only developing a product, but when you face this type of problems that are large scale, that has the social component, that's what we're referring to. So here's a comparison of the system perspective. Again, system thinking, systems engineering, and engineering systems. How they compare in terms of the focus. So for example, system thinking focus on the process, Systems engineering focus on the whole product, and engineering systems focus on both the process and the actual product. System thinking, consideration of issues. Systems engineering solve complex technical problems, and engineering systems solve complex interdisciplinary technical, social, and management issues. So again, the social component is a big part there. System thinking, evaluation of multiple factors and influences. Systems engineering, develop and test tangible system solutions. And then engineering system influence policy, processes, and use systems engineering to develop system solutions. So again, that social component is present there in terms of developing policies that are put in place by governments so they can find solutions to these large-scale problems. And then finally, inclusion, systems thinking, inclusion of patterns, relationships, and common understanding. Systems engineering needs to meet requirements. So that was one of the things that we want to understand the problem. We want to make sure that we understand the requirements of the customer so we can meet them and measure them to solve the proposed problem. And then engineering systems integrate human technical domain dynamics and approaches. So it's not necessarily looking for a solution for the problem. We want to develop policies so we can change probably the behavior of the population so these things can be limited, such as the problem that we just discussed. Okay, so moving forward, now, yes. Yes. This one? Yeah, yes, go ahead, sorry. If I'm moving too fast, just let me know. And again, I'm recording the lectures, so if you at some point feel that you have to go back, you can refer back to the videos and get some of the notes.
Where are the videos?
You go to tracks on the overview, the main page, and you'll see at the bottom of the description of the class, there's a couple of links there right now. Yeah, no problem. Any other questions? Okay, so I'm gonna try to do that every time, but sometimes the system does not cooperate, and now I will not be able to upload the video. But as long as the computer works, then we will have the video. So the engineering systems view, system domains. As I mentioned at the beginning, we are the discipline of collaboration, if you can see it that way. We want to make sure that all these fields collaborate in a way that we can achieve our goal. So the engineering systems view encompasses not only traditional engineering disciplines, but also technical, management, social, political, legal, and human domains. Okay, so we are going to be dealing with people from different fields, and want to make sure that we are the ones who connect all this expertise in order for us to be able to find or design our system to get a solution. So in this slide, we have a picture that has most of the most commonly known engineering disciplines, and also there's sales, marketing, customer requirements, manufacturing, and so on. So combination, right? We want to make sure that we are capable of dealing with all these fields in order for us to find the solution for our problem. So the traditional approach to systems now encompasses a growing domain breadth. So it's not just engineering, but again, management, legal, human, social, technical. So most like a Rubik's Cube, the domain phases are now completely integrated into the systems engineering perspective of the big but complex picture. So this is one of the things that we have to know. We are not an individual's discipline. We are the discipline of making everybody collaborate and come together into a finding a solution for a problem. So the systems domain phases showing the figure include not only the engineering, technical, and management domains, but also social, political, legal, and human domains. These later softer dimensions require additional attention and research to fully understand their impact and utility in system development. So, so not only the traditional areas, but also these non-traditional areas are also important in our understanding of finding a solution for a problem. So that was about system domains. So we have to have some understanding of these areas. Now we're going to talk a little bit about systems engineering fields. So engineers, specialists, look at systems engineering with a perspective more strongly from their engineering discipline. So if you are a double E, you're going to be looking at systems engineering from your point of view. And that most of the time, when you ask a system, an electrical engineer about systems engineering, they're going to think that you're referring to computer engineering. That's most of the time. And that's the understanding are going to come from their own individual profession. So similarly, since systems engineering is a guide to design of systems, often exercised in the context of a project program, the functional project and senior management will consider the management elements of planning and control to be the key aspects of system development. So if you are looking from a management point of view, then they're going to think about systems engineering from that point of view, from the management perspective. Okay, so the management support functions that are vital to systems engineer success, such as quality management, human resource management, and financial management, can all claim an integral role and perspective to the system development. Okay, so they are not the only components, but they are integral in the design and the solution aspect of the problem. And we discussed at some point that there's a high overlapping between systems engineering, management, and industrial engineering. So at this point, we are focusing on that management component. But if you're an industrial engineering, you know that you're familiar with quality, you're familiar with human resource management, and so on. And there's also a financial component within it. Here's a good picture. There's some examples of systems engineering fields. In that diagram, we have systems engineering in the middle, kind of in the middle. And then we have the overlapping with other fields. You see there's a very large component that is management. And then you have human resources, quality, architectures, control systems. Engineering fields is also a major part of it. Modeling and simulation, operation research. So these two are highly regarded as part of industrial engineering. Project management as well. So as you can see, a big component of the field is coming from management. It's a combination between management and engineering, but there are other areas as well. So the operation research, for instance, how many of you have taken that class, operation research, IE 3340? The view of systems engineering includes provision of a structure that will lead to a quantitative analysis of alternatives and optimal decisions. So operation research, you can formulate a optimization model that can have some constraints that will limit the resources, for instance, that you have available for your system to be built. And then you're going to have an objective function that is going to guide the design in terms of cost, for instance, or profit. So that's what we're referring to here as operation research. In diverse areas such as manufacturing to autonomous systems, another interpretation of systems engineering comes from engineers who develop control systems, who lean heavily on the systems engineering principles that focus on management of interfaces and feedback systems. So if you are developing like something like a robot, then you need to know some type of programming language in order for you to be able to use the information from the sensors and information about the actual movement of the robot to design the instructions and design how the robot is going to respond to the information that you're getting from the environment. So that's what we're referring to here in terms of manufacturing and autonomous systems. So there's a systems engineering part that focuses on the management of the interfaces, such as those sensors that are gathering the data from the environment, and the feedback system. So if you get this information, how is the control is going to react to that information? How is that going to affect the movement, or if you're grabbing something and moving it to another station, for instance? In terms of modeling and simulation, this is another field that is discussed within manufacturing and in industrial engineering. Provides a perspective that is integral to a cost-effective examination of system options to meet the requirements and needs of the users. So I think as engineers, and this is a question, why do we need models? Why is it important for us to be able to develop models? Any type of model, simulation, mathematical. Why models are so important? Yes.
So we can figure out if the system is going to work without putting money into it.
Yes, exactly. So the model allows you to test your solution without actually having to go into the actual system and spend money, like high amounts of money, or stopping your actual operations to test a solution or to build a solution into your system without knowing if it's going to work, right? So you're by developing models, you're basically testing all these ideas without actually having to impact the actual system. And then if the model gives you some good understanding of some good solutions for your problem, then you can implement those. But having that backup information in terms of knowing whether it's going to work or not. So really good. So that's why modeling and simulation is important for us in industrial and manufacturing. We want to make sure that, for instance, if we're going to add a new machine to our production system, and this machine is going to be producing parts faster, how is that going to impact the actual operation of the line? You're changing one machine. If that machine is faster, that doesn't necessarily mean that you're going to be producing faster. So if that machine is part of the line, most likely you're going to have a queue at some point, or you're going to have an overutilization of some of the stations. So you want to know what's going to happen before you actually implement the solution or buying that machine, to see whether or not it's going to have an effect in terms of your production or profit and so on. So I want you to work or answer this question based on what those three examples that I have mentioned. This is going to be lab number 2, and you're going to be working individually. From this group, and based on your current understanding of systems engineering, I already picked manufacturing, operation research, simulation, modeling and simulation, but there are other areas here that you might be familiar with, or maybe there's other areas within your field that you're familiar with. Based on your current understanding of systems engineering, can you identify and justify 3 other disciplines that overlap with systems engineering and give examples on how these disciplines contribute to solving complex problems, complex systems problems? So again, you can pick, let's say, quality or human resources, project management, they're coming from here, that's fine. But based on your current understanding of systems engineering and based on this discussion that we have about the 3 other ones, I want you to pick other 3 disciplines and answer this question. Basically, give something like this. So if you pick human resources, you can say provide this, and that's why it's important. Okay, so I'll let you think about it. You can just open a Word document and type your answers there. And I'm going to, I think there's a link already. I'm going to give you a link so you can upload your answer. Any questions? So let me do that link